Hey everyone, welcome to your first flipped lesson on evaluating limits analytically. And we're going to be talking about some basic properties of limits. Alright, so first of all, we already know that the limit of a function as x approaches c does not necessarily depend on the function value at c. However, we have seen that the limit actually is equal to f of c sometimes, and this implies that the function is continuous at c. This also means the limit can be evaluated by a method called direct substitution. And you're all familiar with what substitution is. So let's take a look at some basic limits. The first one being that the limit as x approaches c of some constant function b is just equal to the constant function b. So as an example of this, let's just take a look at the graph of y equals 4. If that's my function, and I want to, let's say, evaluate the limit as x approaches 2 of that function 4, well, the limit is just 4. All right, second, the limit as x approaches c of the function x is simply just the value c. So just to draw that graph, let's say we look at the graph of y equals x, and I want to evaluate the limit as x approaches 1 of the function x. Well, the limit as x approaches 1 is equal to 1. Third, the limit as x approaches c for some function x to the power n. This is simply equal to c to the power of n. So as an example, let's take a look at our basic cubic function. So this is y equals x cubed. The limit as x approaches, let's say, 2 of the function x cubed is simply equal to 2 cubed, or 8. And this is, of course, when b and c are real numbers and n is a positive integer for that exponent in example 3. All right, so some properties of limits. First of all, we need to let b and c be real numbers. N, for my example, will be a positive integer, and f and g will be functions, and I'm going to define their limits as follows. The limit as x approaches c of my function f, I'll call it L. And the limit as x approaches c of my function g, I'll call it K. Just so we have some values to define those limits for the 5 properties that are to follow. The first property is the scalar multiple property. And this says the limit as x approaches c for any scalar multiple b multiplied by a function, so let's use f in this example, is simply going to be the value of the limit of f at that, as x approaches that point c, multiplied by that scalar, b. Pretty intuitive, hopefully. The sum or difference property. This one states that the limit as x approaches c of the sum or difference of both of our functions f and g is simply going to equal the sum or difference of the values of their limits, L plus or minus K. All right, the product property states that the limit as x approaches c of the product of my two functions f and g is going to equal, what do you think? The product of the values of their limits, L times K. The quotient property states that the limit as x approaches c of the quotient of f and g is simply equal to L divided by K, provided, of course, that K is non-zero. All right, I'm going to scroll down and talk about that fifth and final property, the power property. And the power property is obviously talking about exponents. And it states that the limit as x approaches c of a function raised to a power n, remember n being an integer, is simply equal to the value of the limit L raised to that power n. Let's just do a quick example. Let's say I want to evaluate the limit as x approaches 2 for the function 4x squared plus 3. I'm going to look at this using direct substitution because I know it is a continuous function. So I can say the limit as x approaches 2 of my function 4x squared plus 3 is simply equal to the value at c. So 4 times 2 squared plus 3, which is equal to 19. Sometimes things won't be as easy, and we're going to have to break down a function to evaluate the limit using the limit properties. So let's go ahead for this example and use some of the limit properties to break this function down a little bit. So if I'm evaluating the limit as x approaches 2 of 4x squared plus 3, I could actually go ahead and rewrite this using properties and say that this is equal to the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. All I did here was break this up and use the sum property. To continue further, notice we have a factor of 4. So we have a scalar of 4. Using the scalar property, I could rewrite this again as 4 multiplied by the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. In the end, now we can go ahead and evaluate these limits using direct substitution. So I have 4 multiplied by 2 squared plus, as we saw before, the limit of a constant function is just that constant, and we still get a limit of 19. Okay, awesome. We'll practice this a little bit more in class, but let's continue and talk about when we could use direct substitution. So there's a few theorems in your text, namely theorem 1.3, excuse me. So theorem 1.3, which talks about using direct substitution for limits of polynomial functions and rational functions. So limits of polynomial and rational functions. So an example of this, and make sure you're kind of writing small enough to fit all this on the PowerPoint page. An example of this would be evaluating the limit as x approaches 1 for the function x squared plus x plus 2 over x plus 1. This is a rational function, and we can go ahead and use direct substitution here to evaluate that limit. And the limit is simply equal to 4 over 2, which is equal to 2. All right. Another theorem that you see in your text would be Theorem 1,4. And this talks about using direct substitution for limits with radicals. So limits of functions with radicals. I'll just abbreviate by saying rad functions. So limits of functions with radicals. So the example I'll give for this will be simply evaluating the limit as x approaches 8 of the cube root of x. In this case, the limit exists, and we can evaluate it by substituting in 8 directly for x. The cube root of 8 is 2. One more example. In your text, you'll see a lot about trig functions. So evaluating limits of trig functions. So just a quick example here. Let's just take a look at the limit as x approaches 0 of the tangent function, tangent of x. We can use direct substitution and evaluate this at 0, and tangent of 0 is 0. So the limit as x approaches 0 of tangent of x equals 0. Just to make a quick note about all the theorems I listed above, direct substitution only works provided that the x is approaching a c that is actually in the domain of the function. So it works provided that the x is approaching a c in the domain of the given function.